Hello everyone. My YouTube user account is Christian Huygens, huygensPhysics@gmail.com. My Twitter account is @HuygensPhysics. Today's topic is, could black holes and neutron stars be candidates for dark matter? According to scientists, there's about 5 times more dark matter than ordinary matter in the universe. I've estimated that the total mass of black holes and neutron stars is approximately 70 times larger than the total mass of all the stars and 7 times larger than the total mass of all the ordinary matter. I also estimated that the combined total number of black holes and neutron stars is about 5 times larger than the total number of ordinary stars. In this video, I will try to explain how I did this. Don't expect a fancy video with nice images. According to the image, for every star that is larger than 10 solar masses, there are 260 smaller sized stars. Massive stars live much shorter than smaller stars. Let us assume that on average a massive star, more massive than 10 solar masses, lives 10 million years and then collapses into a black hole or a neutron star. The universe exists for 13.8 billion years. The first stars were formed about 400 million years after the Big Bang, so there's star formation going on for about 13.4 billion years. These are 1340 periods of 10 million years. I now make an assumption. I assume that the number of massive stars has been constant over time. This is not exactly correct because in the beginning there was more gas in the universe than there is now, so you would expect an exponential decline. However, there are other factors that influence star formation. For example, the magnetic fields of galaxies prevent gas from falling into the star-making regions of galaxies. Still, I will assume that massive stars have been formed at a constant rate. Imagine a massive star is born 13.4 billion years ago. It burns for 10 million years and then it dies. Immediately another massive star is born that burns for 10 million years and it dies. If this process is repeated for a total of 1340 times, then we arrive at present day. So for every single massive star that exists today, 1340 massive stars have been born and burned up their energy and have collapsed into black holes or neutron stars. 1 out of every 261 stars is massive according to the image. So for every 260 stars that we see today, there are 1340 black holes or neutron stars. So for every 2 stars that we can see, 10 black holes or neutron stars have been formed. In our galaxy of 100 billion stars, there would have formed about 500 billion black holes. Some scientists estimate that the number of black holes in our galaxy could be about 100 million. I don't know where they get this from, but I can make a guess. We observe 1 supernova per century per galaxy on average. So in 13.4 billion years, we would have had 13.4 billion divided by 100 years is 134 million supernovas in our Milky Way galaxy. A part of this number leaves black holes and the rest leaves neutron stars, so they might assume there could be 100 million black holes. This is incorrect. According to the image, the distribution of stars is as follows. 200 stars between 0.08 and 0.5 stellar masses. I assume the average is 0.25 stellar masses. 50 stars between 0.5 and 2 stellar masses. I assume the average is 1.25 stellar masses. 10 stars between 2 and 10 stellar masses. I assume the average is 6 stellar masses, and 1 star between 10 and 150 stellar masses. Now assume that the average mass of a massive star is 20 solar masses and that the average mass of all the black holes and neutron stars that are formed is 10 solar masses. I assume that the rest of the star explodes away in a supernova or is blown away by the solar wind. Now I calculate the mass percentage of the black holes and neutron stars with regard to the total mass of black holes and neutron stars and the total mass of ordinary stars. Here I show how I calculated that the total mass of black holes and neutron stars is 70 times larger than the total mass of all the ordinary stars. The mass percentage of black holes and neutron stars is the mass of all the black holes and neutron stars divided by the mass of black holes and neutron stars plus the mass of ordinary stars. The mass percentage of black holes and neutron stars is 1340, which is the number of black holes per massive star, times 10, which is the average mass of a black hole or a neutron star in solar masses, divided by 200, which is the number of small stars per massive star, times 0.25, which is the average mass of small stars, plus 50, which is the number of average stars per massive star, times 1.25, which is the average mass of average stars, plus 10, which is the number of large stars per massive star, times 6, which is the average mass of a large star, plus 1 times 20, which is the average mass of massive stars, plus 1340 times 10, and this we multiply with 100% and we get 98.6%. The mass percentage of the black holes and neutron stars with regard to the total mass of black holes and neutron stars and total mass of ordinary stars is 98.6%. So the rest, 1.4%, is the mass percentage of ordinary stars with regard to the total mass of black holes and neutron stars and total mass of ordinary stars. So the total mass of black holes and neutron stars is about 98.6 divided by 1.4 is 70 times larger than the total mass of all the stars. This is a simple rough estimation that excluded some factors, but could black holes be a candidate for dark matter? I have made two equations to calculate the total mass of all black holes and neutron stars and solar masses. I've probably made some mistakes as I made this very quickly. Let me know if I did something wrong. One equation has an integral and the other has a summation. It's more practical in my opinion to use the second equation. According to this image, the total mass of all dark matter is 46 times larger than the total mass of all stars. I calculated the total mass of black holes and neutron stars to be 70 times larger, so I am not that far off. Why do we see so few supernovas? 1 out of every 260 stars is large enough to go supernova. There are 100 billion stars in our galaxy, so there are about 100 billion divided by 260 is 380 million massive stars in our galaxy. Let's assume they burn up their energy in 10 million years on average. That means that we should observe 380 million divided by 10 million is 38 supernovas per year. If all massive stars eventually go supernova, that's about 3 supernovas per month in our Milky Way galaxy. However, we observe about 1 supernova per century per galaxy on average. That is about 3,800 times less than we would expect if all large stars end up going supernova. How can we explain this? There are several explanations. Mass loss because of stellar winds. Very large mass loss in stellar winds in the late stage of stellar evolution can greatly reduce the mass of a star before it finishes burning its thermonuclear fuel. Eventually, the star doesn't have enough mass to collapse into a neutron star and go supernova. Another one is rotational spinning speed of the core the moment that the bounce occurs is too low, and when the core of a massive star is too large, it will not produce a supernova. Rotational spinning speed of the core the moment that the bounce occurs. When the core of a massive star collapses, the rotational spinning speed will increase hugely. Compare it to a figure skater that is turning and pulls her arms and leg to the inside. She will spin much faster. This is because of conservation of angular momentum. The same will happen with collapsing cores of stars. When the star collapses to a ball of neutrons the size of a city, a bounce will occur that will blast the matter into space. The bounce due to degeneracy pressure is possibly not strong enough to overcome the huge gravitational forces. The bounce together with the centrifugal forces might be enough to overcome the gravitational pull and allow a supernova to take place. So the collapsing core must spin fast enough to make a supernova possible. Imagine an iron ball in rest and we drop a magnet on it from a small distance. There's a good chance the magnet will stick. Now imagine the iron ball spinning very fast. Now we drop the magnet on it again. There's a good chance the magnet will be blasted away. Let's take a look at millisecond pulsars. These are pulsars that rotate around their axis within a millisecond. A pulsar has a radius of about 15 kilometers and a circumference of about 90 kilometers. We can easily calculate that this pulsar rotates at a speed of 90,000 kilometers per second. This is about 30% of the speed of light. So I expect that this pulsar was rotating fast enough to go supernova when the bounce happened. Type 1a supernovas. I have made this drawing myself. It is a magnificent piece of work. As you can see, I have incredible paint skills. Now let's take a look at Type 1a supernovas. A white dwarf star and the red giant star are revolving around each other. In my drawing, the red giant star is actually orange. The white dwarf has a yellow accretion disk. Electron degeneracy prevents the white dwarf from further collapsing. Matter of the red giant falls on the white dwarf. This adds to the angular momentum of the white dwarf star. The white dwarf star turns faster and faster as more matter falls in. When the white dwarf star reaches a mass of 1.44 solar masses, the gravitational forces overcome electron degeneracy pressure and the white dwarf star starts collapsing until it becomes a neutron star. The neutron degeneracy pressure causes the core to bounce, and because of the extra added angular momentum, the core spins fast enough to make the star go supernova. A huge explosion occurs. Type 1a supernovas are called standard candles because they are used to measure distances in space. So this type of supernova supports the claim that the collapsing star needs to spin very fast to make a supernova possible. When the core of a massive star is too large, it will not produce a supernova. Let me tell you first something about the Schwarzschild radius. The Schwarzschild radius is the radius of the horizon of a black hole, which depends on the mass. It's the region from where even light cannot escape. There is a linear relationship between the mass of a black hole and its Schwarzschild radius. When the mass of a black hole doubles, the radius doubles. When the radius doubles, the volume doesn't double. The volume increases eightfold, and that means that the density of a black hole decreases with a factor 8. There is an inverse relationship between density of a black hole and r to the third. R is the radius. The volume of a black hole is defined by the volume enclosed within the Schwarzschild radius of a black hole. A neutron star is an object with a huge density. The density ranges between 3.7 times 10 to the 17th kilograms per cubic meter and 5.9 times 10 to the 17th kilograms per cubic meter. A neutron star is an extreme object. It bends space and time considerably. It is not far away from being a black hole. Let's take a look at a neutron star that is increasing in mass. When the mass of a neutron star increases, its Schwarzschild radius will increase as well. The Schwarzschild radius will increase faster than the radius of a neutron star. Let's imagine that we keep adding mass to the neutron star so that the Schwarzschild radius keeps increasing. At a certain point, the Schwarzschild radius will be larger than the radius of the neutron star. The neutron star has become a black hole. We can calculate at what mass this happens. The density of an object can be calculated with the following formula. Rho is the density, m is the mass, and v is the volume. So density is rho is m over v. The volume of a black hole can be calculated with the formula 4/3 pi r to the third, where r is the Schwarzschild radius of a black hole. We insert this in the density formula. Now the density rho is m over 4/3 pi r to the third. The Schwarzschild radius of a black hole is defined by the formula 2gm over c squared. We insert this for r, so now we get rho is m over 4/3 pi 2gm over c squared to the third. Now let's solve this formula for m, the mass of the neutron star. Okay, now we are solving this for m, and eventually we get that m, the mass, is the square root of 3c to the sixth over 32 pi g to the third rho. C is the speed of light, and g is Newton's constant. And okay. And the only variable that we have to fill in is the density rho. The density of a neutron star ranges between 3.7 times 10 to the 17th kilogram per cubic meters and 5.9 times 10 to the 17th kilograms per cubic meters. If rho, the density, is 3.7 times 10 to the 17th kilogram per cubic meters, m, the mass, will be 7.1 solar masses. If rho is 5.9 times
10 to the 17th kilograms per cubic meter, m, the mass of the core will be 5.6 solar masses. This is how a supernova occurs. A star runs out of thermonuclear fuel and starts collapsing. It gets smaller and smaller. At a certain point, electrons and protons fuse into neutrons. Neutrinos are released. The core becomes a ball of neutrons the size of a city. At that moment, neutron degeneracy pressure causes the core to bounce very powerfully. This blasts the surrounding matter into space in a supernova explosion. When the mass of a neutron star is larger than 7.1 solar masses, the neutron star will have turned into a black hole. So when a core of a star is more massive than 7.1 solar masses and it collapses, the core will become a black hole before it can become a neutron star. So before the bounce can occur, the core will have become a black hole. Therefore, a supernova will not happen. This is not the case for a hypernova. For hypernova, other mechanisms are at work, and the hypernova can happen when even more massive cores collapse.
Supporting evidence. Oval galaxies. Oval galaxies seem to lack dark matter. It is also known that stars in oval galaxies are old stars in general, and old stars are not massive, because massive stars only last for about 10 million years. So there's not a lot of star formation going on in oval galaxies. So because of the lack of massive stars being formed, there's a lack of black holes and neutron stars being formed. This could explain the lack of dark matter in oval galaxies. How can we prove all of this? We have to look at old galaxies at a distance of more than 10 billion light years with a very accurate telescope, with telescopes much more accurate than the Hubble telescope. Perhaps we could study the rotational curves of these distant galaxies. We have to look at how much ordinary matter they contain compared to dark matter. We know that all the galaxies contained much more gas and other stuff because the quasars that we see are all very far away from us. Quasars are supermassive black holes that are blasting huge amounts of material and radiation into outer space, and the radiation they emit is sometimes more luminous than a trillion supernovas. The closest quasars we see are 2 billion light years away. Thank you for watching. I hope you enjoyed it. If you have remarks or questions, post them in the comment section under the video. There are more topics I would like to discuss, and I will add more videos in the future.